Imagine sealing a cat inside a steel box with a tiny radioactive atom, a detector, and a vial of poison. If the atom decays, the poison releases and the cat dies. If it does not, the cat lives. Classical intuition demands that one of these outcomes must already be true. Yet quantum mechanics says something far stranger. Until the box is opened, the atom exists in a superposition of decayed and undecayed states, which seems to force the cat into a state of being both alive and dead at once. This is the contrast that made Erwin Schrödinger deeply uncomfortable. The mathematics of quantum theory was astonishingly successful, predicting experiments with near-perfect accuracy, but its philosophical implications felt absurd. In the classical world, objects possess definite properties, whether or not anyone is looking. A planet has a position, a clock has a time, and a cat is either breathing or not. Quantum theory shattered that certainty by replacing solid facts with probability waves, descriptions of what could happen rather than what is. Schrödinger designed the cat paradox not to celebrate this strange logic, but to expose what he saw as a crisis. If the equations truly apply to all matter, then microscopic uncertainty should scale upward into the visible world. The boundary between atoms and everyday objects suddenly disappears. That means the same mathematics, describing an electron in many possible states, now seems to govern living creatures, boxes, rooms, and perhaps entire observers themselves. The real hook is not the cat, but the terrifying role of observation. Why should opening a box decide what was real all along? Did the cat's fate remain suspended in possibility, or did the act of measurement somehow create the outcome itself? In one stroke, Schrödinger transformed a simple thought experiment into a direct attack on the foundations of physics, forcing us to confront a possibility more unsettling than paradox. Maybe reality is not made of definite events until something compels it to choose. That unanswered question is where the paradox stops being a clever story and becomes the measurement problem itself. The moment we ask what counts as an observation, a human eye, a detector, an environment, or something deeper, the cat stops being a metaphor and becomes doorway into the contested idea in quantum physics. The box that broke reality imagined placing a cat inside a sealed steel box with a tiny vial of poison, a radioactive atom, and a detector that will shatter the vial if the atom decays. According to ordinary logic, the cat must be either alive or dead, even if no one opens the box. Yet quantum mechanics refuses to respect that certainty. Before observation, the atom is described as a superposition of decayed and undecayed states, and because the cat's fate is chained to that atom, the mathematics seems to force the cat into a superposition as well, alive and dead at the same time. This was never meant to be a cute paradox. In 1935, Erwin Schrödinger proposed it as an attack on the growing probability interpretation of quantum mechanics. He was deeply uncomfortable with the idea that reality, at its core, could be reduced to mere probabilities, waiting for an observer to look. Classical physics had trained scientists to believe that objects possess definite properties, whether or not anyone is watching. A planet has a position, a pendulum has a speed, and a cat surely has a single physical condition. But the quantum wave function tells a stranger story. It evolves smoothly, allowing multiple possible outcomes to coexist in the mathematics with perfect legitimacy. The trouble begins when that smooth quantum description collides with the everyday world we actually experience. We never open a box and find a blur between life and death. We find one outcome, one fact, one reality. That contrast is what makes Schrödinger's cat so devastating. It exposes a fracture line between the equations that predict nature and the world our senses insist upon. If the math is correct, then certainty seems to emerge only at the moment of measurement. But what counts as a measurement? Is it the detector, the box, the human observer, or something deeper hidden inside reality itself? And once that question is asked, the paradox stops being about a cat in a box and becomes something far more unsettling. When exactly does possibility become reality? That unresolved jump is the doorway to the measurement problem. To see why the cat breaks physics, we have to follow the wave function to the moment observation seems to turn possibility into reality. Section 2. When probability replaces reality, quantum mechanics reaches the cat through a brutally simple chain of logic. At the microscopic level, the radioactive atom is not treated as having secretly decayed or not decayed. Instead, it is described by a wave function, a mathematical object containing multiple possible outcomes at once. Before measurement, the theory evolves this wave function smoothly and deterministically, allowing both possibilities to coexist as valid components of reality's description. The detector, poison vial, and cat are then linked to that atomic state, so the superposition spreads upward through the entire system. This is where common sense collides with the equations. In daily life, probability describes ignorance. A coin hidden under your hand is already heads or tails. You simply do not know which. Quantum probability is different. The mathematics does not describe missing information about a hidden reality. It says the system genuinely occupies overlapping possibilities until an interaction forces a single result. The contrast is devastating. Classical uncertainty hides facts. Quantum uncertainty seems to replace facts. The crisis deepens with measurement. The Schrödinger equation predicts only the smooth evolution of the wave function, never the abrupt jump to one definite outcome. Yet experiments always end with exactly one result. We never open the box and see a blurred, half-alive cat. Somewhere between the abstract mathematics and lived experience, possibility hardens into fact. But where? At the detector click? At the poison release? When the environment interacts with the box? Or only when a conscious observer learns the result? This unresolved gap is the measurement problem, and it remains one of the deepest fractures in physics. The equations are unmatched in predictive power, yet they seem silent on the very moment reality becomes definite. Some interpretations claim collapse is fundamental, a real physical process triggered by measurement. Others argue the wave function never collapses at all, and that what we call outcomes are only branches of a larger reality. The cat paradox survives because it pushes this tension to a human scale. It forces us to confront whether the world possesses properties before interaction, or whether definiteness is something that emerges only through relationships between systems. The deeper question is no longer whether the cat lives or dies. It is whether alive and dead were ever meaningful descriptions before anything in the universe had reason to distinguish between them. And once that possibility is taken seriously, the paradox expands beyond a sealed box into a terrifying question. If observation gives reality its sharp edges, what exactly was the universe before anything was there to observe it? That is the contrast framing at the heart of the paradox. Equations insist on continuous possibility, experience insists on singular reality. Section by section, physics can describe the probabilities with astonishing precision, yet still cannot fully explain why one history becomes yours. And mystery remains. Section 3, the experiment that still haunts. Modern physics Schrödinger's cat refuses to die because modern physics still lives inside its question. Today, the paradox is no longer just philosophy. It sits at the heart of quantum computing, decoherence theory, and the battle over what the wave function really means. Quantum computers exploit superposition directly, allowing quantum bits to exist in multiple computational states before measurement selects one output. In a sense, every qubit is a controlled descendant of Schrödinger's cat, engineered not to avoid paradox, but to use it. The first major response is the Copenhagen interpretation. Here, the wave function is treated as a tool for predicting outcomes, and measurement causes a genuine collapse into one reality. It preserves the practical success of the theory, but leaves the collapse itself disturbingly mysterious. Why should observation hold such special authority over the laws of nature? Many worlds removes collapse entirely. The wave function never chooses. Instead, every possible outcome continues in separate branches of reality, with one branch containing a living cat and another a dead one. The paradox is resolved by multiplying worlds, but the emotional cost is enormous. Reality becomes a constantly splitting structure far beyond human intuition. Decoherence offers a more physical bridge. It argues that interactions with the environment rapidly destroy visible superpositions, making quantum possibilities appear classical long before a human observer opens the box.